The first thing I'll introduce myself, Donald Kinghorn. I am the scientific computing advisor at Puget Systems. The doctor part of my name is referring to a PhD in theoretical chemistry back in the mid-90s. I've been doing scientific computing, writing software, and supercomputing, building Linux clusters, uh, forever. seems like I have a lot of background in this work, and from writing code to building clusters, including a couple of top 500 supercomputers that I was involved with. So uh, this is my world. Um, the first thing that maybe you should notice here is that the title is now a little bit augmented. When I originally found out I was going to do this, it was like, okay, well, let me talk about the Threadripper performance for high performance computing, and which is really interesting. But I have been able to augment my results with a new Xeon, the Xeon 3265W, that's Cascade Lake Xeon. And I was able to run all the same testing on a dual EPIC 7742 system. So the comparison results in here will be a lot better than originally planned. Um, I think you'll find some new information here. I'll start with just a little introduction about who we are, and then I'll talk about the systems that are under test. There's 4 of them now. A little bit about what actually used for the testing, and then into the good stuff, the charts and plots. And there's lots of those in there, and I'll try to get to it quickly because there's lots of opportunity for discussion there. Oh, this would be great if, oh, phew. Okay, sorry, I've got some lag here. Um, okay, I've pretty much described what the purpose of the webinar is. I'm looking at high performance computing. I'm looking at scientific computing aspects of these processors. This is 4 of the best processors out right now. These are really good, um, appropriate for high-end workstations and server nodes, whatever. This is really good stuff. So this was fun testing. But what we're looking at here is specifically for the performance, the number crunching aspects of these things. So we're looking at double precision floating point performance, parallel scaling. We've got lots of cores here. And really, really importantly, we're looking at memory subsystem performance. And we will have questions. If you have questions, you can use the Q&A thing down there at the bottom, and that'll open a panel for you. I'll try to do questions at the end, and I'll try to save time for it. I'll try to be sure I can get some stuff answered. The first thing I want to say is who we are, Puget Systems. Puget Systems has been around for really about 20 years now. We specialize in high-performance workstations for a variety of uses. Of video production, post-production is real. We're really experts at that. The scientific computing, machine learning, AI, engineering applications. That's our focus, and our focus is really on not just providing generic hardware, but actually trying we're a company that is big enough to have an influence on the industry, but we're small enough that we still focus on the individual customers, individual users. So we try to tailor our systems and our testing for what you actually really need to do. And we pride ourselves on that, and that's actually a huge motivator for me, because it's personally knowing that I'm helping people do their research, do their work. That's very satisfying to me, and that's part of the reason I'm here. In fact, I've been here for going on 8 years now, so I kind of like the place. We're very, very particular about components that we use, and we don't pull any punches about our reviews and our recommendations. We try to really give people the best tools for their work. Website is easy to find. It's PugetSystems.com. Just a comment on the name. Puget is referring to Puget Sound. We're south of Seattle, near one of the beautiful waterways of the world, the Puget Sound. So that's, a lot of people have trouble with the pronunciation there, but it's Puget. Okay, a great part of our website, of course, is the HPC blog. If you go to publications from our main navigation menu, you'll find there's a lot of great stuff. We put out a lot of content. The HPC blog is where I do my writing. I've got several articles, recent posts on the Threadripper, which is just amazing processors. But you'll find stuff from me there that ranges from simple to very complex, and how-tos, system configuration, kind of how-tos, and so check it out. There's some good stuff there, and the content of this webinar will probably wind up in a post soon. So you might want to keep an eye on that. Now, what are we actually looking at? The first thing, and what originally I was focusing on, and still am, are the new AMD Threadripper processors. This is the 3990X and 3970X. That's a 64 core and a 32 core. These are really interesting processors. They have the clock frequencies here that are listed. The first number is essentially the max turbo, the highest basically single core performance, and then the second number is usually not reported by manufacturers, which is kind of frustrating. But this is what you expect to see when all cores are loaded. So this is the all-core turbo, and this is the most useful number to have when you're looking at a processor, is the all-core turbo, because that's what it's really going to be doing when you're running it under heavy load. Both of these systems were running on the same platform, a nice gigabyte motherboard that we have found for this. Both of these systems have 128 gigabytes of memory in it with 8 modules. I want to point out, and this is something to remember, that these processors, looks like these processors have 4 memory channels. That will become relevant. The software that these things are running, I did testing with a pre-release of Ubuntu 2004, which I'm using personally for a lot of things. This was the installs for these were simple server installs, but I did this because I wanted to get up to date. I wanted to have a system that is AMD EPYC aware, that's aware of the Zen 2 core processors. So I wanted GCC compilers that have Zen 2 flags. I'll talk about the actual applications, but here's basically kind of a list. I'm using the AMD Bliss library where it's appropriate. This version 2, so this has Zen 2 optimizations. The LinPack is basically included along with the Bliss library. I'm running a high performance conjugate gradient for the first time I've been reporting results. This turned out to be really interesting. This is compiled from source using local architecture optimizations. I've got MPI needed in here mostly for header files, and using AMD molecular dynamics code, and Anaconda Python, NumPy, with some variations in the BLAS library underneath that. A new one here is the Intel 62 or 3265W. This is a really nice processor. This is Cascade Lake. It's new. This is the 24 core version. There is a 28. Again, it has a similar turbo clock and all-core turbo, so it compares well with the Threadrippers. The thing that I like the most about this particular system is that it's on a fantastic motherboard. And you'll notice this little 64L here. This is a setup that has 4x16 PCIe slots without any PCIe switching. So there's no PLX chips. This is a great board for multi-GPU use, and that's mainly our intention for it. This system I've got loaded up with 32 gig modules, so there's 192 gigs in there because there's 6 modules. And this processor has 6 memory channels. Again, kind of make mental note of that. The system that I'm running here is essentially the same image that I was running with the Threadrippers. But I'm using Intel MKL library, the math kernel library for underlying BLAS libraries. And LinPack is from that. And everything, and I've got some kind of interesting testing here with various libraries on here. So you can see kind of the effects of the different architectures. I should point out that the Xeon processor, and this is relevant to our work here, for this presentation, this has an AVX 512 vector unit. The AMD systems have an AVX2, which is a 256-bit vector unit. Intel has a bit of advantage here, but it's not as big as what you might think. Now, this one here, I really wanted to have EPYC in on the comparisons here. We are at Puget Systems, we are in the process right now of qualifying hardware for platforms to offer EPYC-based systems. Really excited about that. I'm especially excited about doing single socket EPYC. Yeah, they're going to be really nice. But what I'm running here, because I don't have access to this stuff yet, I'm running this on Microsoft Azure using an HB120 RSV2 instance. And this is a EPYC Brougham processor, very, very good. This is dual 64, but there's 4 cores on each of those that are reserved for the cloud service underneath. So there's really just 120 cores available, and those are real cores. They have SMT threading off because this is intended for real serious high compute. You'll see. Lots of memory in here, 480 gigabytes of memory available. This system, I'm using their Ubuntu 1804 image, but all of the software that I'm running, all of the codes were built with Zen 2 optimizations using the updated compilers, even though the native compiler there on 1804 would have been 7.5, but everything is built with 9.2. So this is really running the same code as the Threadripper. Now, okay, so that's the systems. These are all great. Now the software. The first up is the HPL, the High Performance LinPack. This is my favorite benchmark ever. I've been running it for seems like forever. It is generally extremely well optimized by vendors, by the hardware vendors, the CPU vendors. This is what is used for ranking the systems on the top 500 supercomputer list. When you see all these crazy, you know, how many petaflops or exaflops we're moving into, that's what they're referring to, is the performance they got out of the HPL benchmark, the LinPack benchmark. It puts an extreme load on the processors because it's highly optimized and it takes advantage of every little trick in the processor. So it definitely takes advantage of vectorization like the AVX units. For the AMD systems is built against the AMD this library. That's the underlying numerical computing library. It's the BLAS library. That's the basic linear algebra subroutines. That's where you get all the things like DGEM, the matrix multiplies. This stuff is highly optimized for architecture. I used problem sizes that went over 80% of the total memory on the systems. So for really for all of the test runs, I ran this with 114,000 equation. LinPack is a equation package. LinPack and IcePack were the preceded LAPACK, which is numerical linear algebra library now. On Epic, because I have so much memory and I wanted to try to get better performance, I actually bumped that up to 200,000. So, you know, which is staggering. And I did performance tuning. When you're doing this stuff on a supercomputer for benchmarking, you can spend, a whole team can spend weeks trying to get optimal numbers. I did not do that, but I did run tuning things, and I found kind of surprising. These are block matrix routines for a level 3 blast with matrix, and I found are actually really pretty large Intel. I used the highly optimized Intel benchmark HPL benchmark from the MKL, the math kernel library. That's what provides their BLAS library and their LAPACK and all that. And this is the threaded version. So this is OpenMP thread. The AMD stuff I also ran with was multi-threaded, but I used the but I needed the MPI headers and stuff like that. And so it was tuned like it was MPI, but it was running multi-threaded. And that actually had given me the best performance. Okay, change. Oh, yeah, I do have a little lag here. Sorry about the next thing I looked at, again, this is Python code. This is a simple matrix norm. It's a Frobenius norm. I love saying that. It's a norm of a matrix product. And so this again is measuring kind of low-level performance. The NumPy library is the numerical Python, NumPy if you like it to be called that. It's a standard numerical library for Python. It's tremendous. It's part of the reason that Python is so useful. But it uses underlying BLAS library, so it calls the optimized routines, and so that's why it's tremendous performance. This is how Python gets such great numerical performance. The problem size here, basically I have two matrices that are 20,000 by 20,000, and they're random matrices and they're set up as float 64, so they're double precision. And then I'm calling NumPy linear algebra routines, calling norm. And this nice little shorthand here is matrix multiply. So it's A times B and then computing that norm. And that's basically like this square root of this trace over here. Again, this is very heavy matrix operations. So it's testing floating point, again, really heavily. And I tested with two different BLAS libraries. I tested with OpenBLAS for AMD. That gave me the best performance. I tested with MKL for Intel, and I did a little extra interesting stuff in there. You'll see. Okay, this is a new benchmark. I hadn't run this in the past, and I kind of kicked myself for not doing it. I was always concerned about optimizing some of the subroutines that are called in it. But this is a high performance conjugate gradient call code. This is a new benchmark for the top 500 supercomputer list, and it's great. This benchmark is memory bound. So it is a good benchmark for checking IO and memory throughput performance. And what is actually going on here with this, LinPack is a set of linear equations being solved. This here is basically a sparse second order partial differential equation solver. It's using a multi-grid solver with a conjugate gradient approximation. It's second order, so the conjugate gradients are usually used to provide approximations for second derivatives, so a Hessian matrix. This is a great problem. There's a large number of problems in physics simulation, engineering simulations, fluid dynamics, finite elements, stuff like this, that are weight mechanics. A lot of things wind up being second order differential equations. Good benchmark. And it's a system, and it's sparse. It really stretches the memory performance. So this was eye-opening. The next one here, I'm taking a little more time. It's great scalability, and it doesn't critically depend on more of the real world. There's a lot of programs that really behave this way. It's a great program. Jobs, they're both pretty large, 92,000 atom, this lipoprotein computing forces, and that's about 1 million atoms. This is a huge calculation. Right now that there are surely running the coronavirus simulations program, and it's great on workstations. Performance is tremendous. Also has very good show some of that. This requires, for best performance, you need okay. Now the good stuff. Okay, the first thing here is the LinPack benchmarks. Now, I've got the systems that are actually under test, but I want to give you the perspective on performance is like. The I hope you don't see the 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 processor down at the very bottom at the Intel Core i9 9900A. It's our most popular processor. It's uh, it's it's essentially based on the old new update to this, but it's still based on that same old Haswell core, and it's for really serious number crunching. It's an AVX2 vector unit in there, but it's a great processor, and there's a lot of applications that are just tremendous with it, computing. This just goes right up the list with several. I got the results for that, and the 32 core Threadripper were very close. They have similar kind of characteristics. This result here is highly optimized for Intel because it's using the MKL library. That's got AVX 512. The Threadripper has some more cores, but it's AVX2. It's the Bliss2 library. Very, very similar. I could probably get better performance out of both of these, but this was interesting to me. Going to 64 cores, scaling is not tremendous here. I would like to see more performance out of the 64 core Threadripper, and probably could get it, but I'd have to work harder at it. And then of course, Epic was outstanding. That's about 2.5 teraflops performance on that system. And again, I think theoretical is close to 4 teraflops. But that gives you an idea of kind of the spread of performance that you can see for this kind of number crunching. I wanted to put this slide up because in my blog post on the Threadripper, I talked about the scaling. I did analysis with Amdahl's law, which is basically a law concerning the relative amount of parallelism in an application. You know, there's a limitation to how much performance you can achieve, no matter how many cores you throw at it, how much you throw at it. And so AMD, our Amdahl's law is kind of a reflection of that. But when I put this up, the scaling looks bad, and it's not great because it doesn't scale out all that wonderfully. But I have it relative to the ideal linear speedup, which means like 40 cores is going to be 40 times faster. Well, this is not even possible with these processors because the clock drops as you engage more cores. So this dotted line here is actually kind of an adjusted ideal linear scaling based on that core clock adjustment. So you can see that it's actually not really all that bad. But I wanted you to see that just so you're aware of how that affects things. For NumPy, this is interesting. Of course, this is measuring matrix operations really, and of course the dual epic system did best on this. This problem is probably not big enough really for optimal performance measurement here, but it's pretty good. The next one up here is the 24 core Xeon, and that is using the underlying MKL library. That's the default library with Anaconda Python. That's what things are by default linked against when they need those libraries. But you can change that library, and by default that doesn't give very good performance on the AMD processors. The OpenBLAS actually did really quite well with this, and I didn't test any other kind of trickery here. But here again, you're seeing that the 64 core is performing pretty close to what the Xeon did. And you also see a little number in parentheses here. That's where I got the peak performance. It peaked before it hit 64 cores. The 32 core, it performed really well. It scaled well. It made use of all 32 cores nicely. But these last two things here are, I think, really quite interesting. If I run that Intel processor using the same OpenBLAS that I used for the AMD processors, you see the performance is way worse. And that's how highly MKL is optimized for Intel. There's some trickery that you can do. You can set the MKL debug level to a type 5, which is basically like a Haswell core. And that often works really well with AMD. But you can see kind of here the difference between that drops it down towards using AVX2 instead of AVX512. So you can see that takes a pretty, that gives a performance gain for sure, but it's still pretty big hit against the optimized library. So yeah, kind of takeaways there is that, yeah, this stuff is dependent on what you're linking against. But performance of all of these is actually outstanding. So I'm not complaining here. This mess right here kind of shows how some of that scaling went with that NumPy calculation. And you can see here this result over here, that's the Xeon, and it just kept going up. It just got better and better. It has really good performance, and that was with the optimal library. If you look at this blue line here, that is that same Xeon processor, but using OpenBLAS. Big difference. It's still scaled out pretty well. Okay, but big difference in performance. Using the debug on here, that gave performance out to its total 24 cores, really, really, really similar to the AMD Threadripper processors. Okay, so that's an interesting data point in my opinion. But you can see here what happened with the 64-core Threadripper. It started dropping off. The Epic actually took a little bit of a dip, and then get back there, and then had a nice jump in performance. This performance can be kind of unpredictable sometimes, what you're going to see, but this is what I saw. So now HPCG, high performance conjugate gradients. You're welcome, Ron. There's a few people actually have kind of been bugging me to run this for a while, and thank you, because this is actually a really great benchmark. Of course, this is really limited by memory performance. And these numbers over here, these are gigaflops. So this is still measuring that floating point performance, but you see it's way lower than like LinPack. And that's because this is like a real world application. It's memory bound. It's a really hard case. But the dual Epic did fantastic here. That's because it's got loads of memory channels, and there's two sockets there, two processors accessing that memory. So really quite good. The Xeon, again, it does really well here because it's got that 6-channel memory. So it did well. Yeah, it did well out to its 24 cores. But now take a look at the Threadripper. This is a gotcha on the Threadrippers. You see that the number in parentheses is actually where this thing hit its best performance. So on that 64-core processor, it got its best performance with 16 cores. And with the 32-core, it peaked out at 8 cores. So that's memory performance. There's not enough memory channels to really feed those cores. This is a hard case, and this is a memory bound code. So yeah, it's not the best choice for memory bound. things. Really, really looking forward to getting our EPIC systems together, because they should be way better for this kind of an application. So really looking forward to that. But this is not really a big, um, you know, not really criticizing these processors here because they're great. But that is a limitation for real world here. You can really see what happens here in this kind of scaling plot. Those two Threadrippers basically just come up here and boom, go flat. They just drop. They don't get any better. The Xeon did well and then started to roll over, but it hadn't flattened out yet. Well, it is flattening out at that point, but it improved all the way out to the max cores. The dual EPIC did outstandingly well. There's a little dip here, who knows why, but basically it's way up there. It is just kind of starting to flatten out here. So yeah, that's a pretty interesting chart to look at. If you have a memory bound code, remember this chart. Now, some real world here. NAMD, great application. I love benchmarking with NAMD because it scales really well on CPU. It's an important molecular dynamics code. It's a really good program. I want to show you a couple of interesting things here. The AMD processors did great with this, and this is the case because this is kind of more typical real world performance. You don't always get that great vectorization and this highly optimized performance from underlying library calls. The so yeah, having lots of cores, having more cores was a big advantage there. The Xeon, this is an interesting code too, because in a lot of applications, hyperthreads, as SMT threads, they will often reduce the performance if the CPUs are really, really grinding. But the NAMD is scheduling lots and lots and lots of force calculations. So having that thread staging with the hyperthreads, it actually gives an advantage. It does improve performance here. This is one of those things you basically have to test when you're optimizing your application. It's like, well, okay, is this going to help or not? In this case, it actually was it's a pretty nice improvement here. But this is just great here. The 32 core Threadripper, that's a really nice result in my opinion. Again, this is with the SMT threads on. The 64 core, again, it does really well on CPU only compute. And then of course the EPIC is really, really quite nice. Thing to be aware of here though, for when you have the opportunity to use GPU acceleration, it can make a huge difference. And for this program, it requires lots of cores in order to keep up with GPUs. So these numbers that I've got right here, this is the Threadrippers with two really good NVIDIA GPUs, the 2080 Ti and the RTX Titan. They're essentially really pretty much the same here. In my opinion, kind of the outstanding result on this slide is here, the 32 core Threadripper with 2 GPUs. That's really a good result. That's good utilization of the hardware. This is probably a really good balance between the GPUs and the CPUs. So make note of that. And again, I wanted to put a little scaling plot, Amdahl's law scaling, because I had this in my blog post on the Threadripper. when I looked at the results for Threadripper, I was going, wow, that's great scaling. But I think I just kind of mentally adjusted for the processor clock changes as it goes out to all the cores. So by adding this line here, that's basically just it's adjusted to um, the 64 core Threadripper um, uh, clock scaling. So you can see that, yeah, NAMD just scales really, really well. Yeah, and again, that 32 core just does excellent. It's almost perfect. Now a bigger problem. Okay, that was actually a pretty good sized problem. The 92,000 atoms is a lot. But this virus calculation, this is big. It's 1,000,000 atoms, loads and loads and loads of forces. But again, you see that the Xeon is oh, I should note here. This is the traditional performance measure for NAMD. This is days per nanosecond. That means how many days it will take to compute 1 nanosecond of simulation time. So these are the kind of calculations that run on big systems for a long time. But yeah, the Xeon didn't do all that great. This is where you need the cores. This is an outstanding result here, I think, for the 32 core Threadripper. Again, you get a nice boost going up to the 64 cores, and again, the Epic pays off really nicely because this NAMD just scales really well. It's a great parallel application. And you throw the GPUs into the mix, yeah, it's a lot better performance. And this is kind of similar to what we saw with the smaller problem. There is probably a significant speed up in this case because the problem size is bigger. So the extra cores and a little bit better GPUs here is improving the performance somewhat. There is a significant performance boost here on that Xeon system. That system, I ran that with, I loaded it up with 4 2080 Ti's. That's basically what that platform is designed for. And yeah, the performance is really quite good for a large problem like this. In my opinion, there's not enough cores here to balance with that many GPUs. But it was good. That was a good result. Still, I really like the 32 core Threadripper here. I think this is just a nice utilization of the hardware. These are more expensive systems, and you're not really getting performance value out of that. The 32 core Threadripper with a couple GPUs is just great for AMD. I like it a lot. Okay, a lot of data. Summary. These are all great processors. I hope you really see that from what I presented. The Threadripper, really like it. Excellent processor. I don't hesitate to recommend them. These are really good, and they're only going to get better. AMD is doing great stuff now. The thing that you have to be cautious of here is if you have memory bound performance, you can take problems. You can take a big hit with the Threadripper. We should be able to address that really quite nicely with our new Epic single cores coming up. And the Intel stuff does really well for that too. And also, what I looked at here was these are high performance computations. This is numerical grinding at its hardest. There's a lot of applications that don't really depend on that. So, but this is, and oh yeah, and something I did not look at. Say you've got that 64 core Threadripper. Well, okay, what happens if you just run multiple jobs? Okay, can you get better utilization of the hardware? I don't really know that yet. In general, when I'm running these high intensity calculations, I just want the best performance I can get for the job I'm running. But for workflows, a lot of times you just need to run a bunch of jobs, and you might be able to do that really well with this. And if a lot of this stuff was confusing to you, we're here to help. Um, our consultant, well, oops. This is basically the end of the webinar. Again, ask questions, and please fill out the poll at the end here. We really like getting feedback from you. It's really important. And I just want to stop here, put this slide up. We focused on getting you good systems for your work. And if you can contact our sales consultants, and they will ask you what you are doing. And if they don't have a clue about what you're doing, they will ask me, and I probably will have a clue. I may not, I may not have direct experience with some of the codes that you're running, but I've got a wide experience with a lot of stuff. I pretty much can look at an application and have a really good idea of what's going to be the best kind of platform for running it. So thank you very much. And let's see, I'm going to go ahead at this point and pop up the Q&A. Oh, I don't have a lot of questions in here. Okay, we are kind of over time, just a little bit here. If for all of you that are still with me, I appreciate it, and I will see if I can answer some questions here. 4 TXP cards and dual Xeon system. Old dual Xeon systems, wonderful. Those things are still great. Limitations on PCI, memory lanes, 4 Titan Vs and 1 PC. Oh my goodness. Okay, 4 RTX Titans and another. Oh, this is a long question. Adam, I might have to. You can get a hold of me. You can actually send an email through the sales people, and they'll forward it to me. Maybe I'll help you with that a little bit better. Coming down to the bottom of this is like related to two-socket Roam. Yeah, they're going to be great. I don't have to even read the rest of the questions. It's like, yeah, they're going to be great. And yeah, and I expect to be able to do really good GPU acceleration on those platforms too. So, so that's good. I've got raw compute today, 5-year system deployment. Oh wow, great question. If you're looking at deployments for kind of like that are going to be up and running for a while, live under your desk, no budget. I don't really have a budget. Stuff is only going to get better. The AMD is just doing amazing work right now. I expect some excellent processors coming out from them by the end of the year. Their supply seems to be pretty good. Intel is not just sitting around. They are cranking out good stuff. They will have new processors. They are having some trouble with yields and getting stuff out the door. It's really nice to have choice right now. I don't hesitate to recommend the AMD processors. They're great. The Xeon stuff is great too. The Xeon stuff is more conservative, and it's you can be pretty sure that it's going to be a really good stable platform and it's going to work great. But the AMD stuff looks good, looks really good here. Okay, hopefully I'm answering that. If I have 13 years writing for Intel HPC unlimited threading goal, would you move if it was CPU bound? That's a good question. If you've been optimizing code for Intel for a long time and you're really good at doing vectorization, tuning for vectorization and tuning for the hardware, the Intel tools are fantastic. Their compilers are really good. Their libraries are really good. That's Intel definitely, they have an advantage there. That's really good stuff. If you are really skilled at tuning for Intel, I, you probably are best advised to stick with it. I think AMD now with the new Zen processor, Zen cores are a great opportunity for optimization for people that will roll up their sleeves and get the best out of these processors. Um, the compilers are only going to get better. The libraries are going to get better. But that's kind of what I was saying about being conservative. On the Intel side, you're a little bit more conservative. You've got great tools on Intel. AMD, the tools are not really quite as good. But I expect that to change over time because it's just really good. Hey, Ron. It'd be nice to include epic results using only one socket is it more comparable. Yeah, totally. I fired that stuff up on Azure and ran it, and because I wanted to have those data points, I wanted to see what it was like. Single socket epic running with just one processor. I think that's actually where the sweet spot is going to be for systems going forward, especially workstations. Those are going to be great workstations. And as soon as I get my hands on that stuff, I promise you I will be testing and writing up the results. And I'm not sure of our timeline for getting that stuff. We're very careful about qualifying the entire platform. So there'll be a lot of testing involved. But hopefully that happens sooner rather than later. And okay, I've got a lot more questions coming up. I'm running a little bit long here. I'll see if I can answer a couple more things. Chipset, Intel, and latency. Yeah, the latency between AMD and Intel. I was talking about chipset design here. The AMD design, chiplet. Yeah, the chiplet design that AMD is doing. This is brilliant. The industry is going to follow AMD again on this. This is a really good way to get good yield and get good performance. I don't think that the latency is really all that bad. In like the earlier generations of like the Threadripper, it was not good, and you took a big hit. I think the current processors, the Zen 2 core, and the way they're doing the chiplets now with the interconnect, it looks really good, and I expect it to only get better. So, but yeah, there's definitely a difference there. Intel is not using that kind of design yet. So, and there is some latency there that can kind of contribute to some of the memory problems, but AMD is doing really good design. I'm not too concerned about it. I think the current processors are really, really good, and I think they're only going to get better. Am I willing to provide software support, i.e. compile optimizations? Oh, okay, helping you with compiling your code and stuff like that. You know what, that's actually a pretty, that's, hey, Jim, that's a pretty good question. Um, we are looking at doing more kind of consulting work. So this would not be like a free service, but may possibly be able to do that. But that can be really daunting. Um, what I do try to do for sure is to get good posts up on how to get good performance out of stuff and how to set systems up to work well. Um, specific optimization, compiling support for individual packages, that's going to be tough. But don't think we're not thinking about it, because we absolutely are. More about an AMD, new versions coming out. Yes, always. Um, or is customer completely responsible for all compilers and reconfigurations? NAMD has got a great history of, with their updates, of being really simple to update. This is a great project. NAMD is a tremendous project. Updating the NAMD binary builds on an existing platform should be really straightforward, and it shouldn't give you any headaches. Single socket Epic ETA, I can't give you an ETA on that yet. I'm hoping really soon, because I'm really excited about it, and I think actually everybody at Puget Systems is pretty excited about seeing these Epic systems come up. But we're not going to do things until we know the stuff is great. We have a really good set of stuff. It shouldn't be a problem though, because the hardware, the whole platform is really good. Oh, hey, this is a good question. Price difference between the Epic and the AMD 64. The An interesting comparison here, just on price. I'm not completely sure yet on the Epic. It's going to compare really competitively with Xeon, with the Xeon stuff. The the um, the An interesting comparison. Okay, the Xeon that I tested here, the 64L system, that platform, um, configured out, is really close to the cost of the 64 core Threadripper system. So that's kind of an interesting comparison here. AMD and Intel are going to be head to head going forward, because they're really trying to compete with each other now. So performance wise, either one is going to be good value. AMD or Intel made big price adjustments in order to gain better performance parity with AMD on the cost. AMD 3990X. Okay, I'm not sure what I was wondering about. Okay. Yeah, 3990X. I hopefully I answered your question there. The Epic system, I think these processors are priced really good. I don't know yet how price is going to compare against that 64 core Threadripper and the Epic. The Epic is definitely enterprise class hardware, so I expect it to be priced a little bit more, but the pricing is good. Any chance of better motherboards for AMD 3990? We're pretty happy with what we've got right now. Um, I let's see. Okay, I'm sorry. I had to check a message real quick. Yeah, we're. Okay. Yeah, the motherboards were a problem with originally with the new Zen 2 core processors. We had a lot of trouble. Motherboard makers really didn't do ideal boards for us, and I would have loved to have seen a board that had good 4 for GPU support, but it's really not there. There's one ASRock board that looks really, really nice, but it's there's reasons that we really can't use it. I don't think anybody is going more than 2 GPUs on Threadripper. That's kind of a shame. This will be a big advantage for Epic, and I think Epic is the more appropriate platform for that level. The Epic and the Xeon is going to be the more appropriate platform for a multi-GPU, 4+ GPUs in a system. I'm going to keep going answering questions, although I'm quite over. I don't know if anybody's listening, but this will at least be recorded somewhere. Oh boy, I hope it's recorded. Okay, some people claim. Yeah, the AVX 512 on Intel. This is a great question. It does improve things, but I'll tell you what, AVX 2 is outstanding. It's a really, really great vector unit, and the overall system does not take a big hit when AVX 2 is engaged. AVX 512 has its own clock. So when that vector unit engages, it lowers the system clock significantly. So when it first came out, we were hoping for another, when AVX2 came out, it was like, boom, double the performance. It was great. AVX 512, we're thinking, wow, okay, we got twice the width on the registers here. Hopefully we're going to get twice the performance. No, it's about 40% boost. And that's because the clocks drop. It has to maintain power envelope to keep running right. So AVX2 is definitely an advantage for some codes that are really well vectorized, but it's not a huge leap in the real world over AVX2. I'm curious to see what AMD comes up with to improve their vectorization. I don't think it's probably a high priority for them, but I really hope they come up with something great. I think they will. Any way to increase memory higher than 128 gigs for the AMD? I do believe so. I think, yeah, I think we can use a lot bigger modules in there. I'm not completely sure what the max capacity is, but I'm pretty sure it would be really easy to double that to 256, maybe 512. I'm not completely sure. That would be a great question for our sales consultants. They can answer that right off the bat. I am over, and I hit the bottom of the list for questions, so I am going to go ahead and bail out here, and I will see you all again, I hope.